Participants, now we had the second session from Dr. Anand M. Shivapuji sir, who acted as the chief guest to our FDP program. On first day, he had delivered his first session, and again we are going to, and with an immense pleasure, we are going to listen second session of our next resource person, Dr. Anand M. Shivapuji sir, who is a senior research scientist, the Center for Sustainable Technologies, IISc Bangalore, and he's a founder director for Cops of Solutions Private Limited Bangalore, Chief Technology Officer for BharatNet Systems Private Limited Hyderabad, and founder member for E3 Labs Private Limited Bangalore. And sir completed his PhD from IISc Bangalore. I request our resource person to take over the session.
Thank you, madam. Good evening, everybody. Nice to see you all once again. In this, am I audible, please?
Yes, sir.
You are audible, sir.
Okay, yeah, thank you. In this session, I will take you all through a different but interesting route for generating hydrogen. This will be through biomass. Let me just project my screen. Somebody can confirm my screen is visible, please?
Yes, sir, it is visible, sir.
Okay, thank you. So the title of my talk today will be Green Hydrogen and Green Chemicals. Basically, a carbon negative bioresource pathway. Okay, so this is broadly, I will be talking about this. While the focus will be on hydrogen, I will be showing an example of hydrogen generation, also some results for LCA. I will also be touching upon how green chemicals also can be generated. Because the hydrogen ecosystem is still yet to be established, but green chemical ecosystem is already well established and can actually lead to immediate greening of the energy sector. Yeah, just a brief of myself. I am Dr. Anand Shivapuji, senior research scientist working in Indian Institute of Science in the laboratory by the name Combustion, Gasification and Propulsion Laboratory. This laboratory basically deals with thermochemical conversion of biomass into various end chemicals, and then they use in a number of downstream applications. Okay. We'll touch upon a few of those things as we move along. Now, I have already discussed about this particular concept, that is the representative concentration pathway, during my inaugural address. Okay. Today we will briefly touch upon that particular representative concentration pathway analysis, because that is going to lay the foundation for understanding why bioenergy is critical. Okay. Recollecting some of our discussions, would like to draw your attention to the fact that we have looked at 4 different representative concentration pathway possibilities or models. They are RCP 8.5, RCP 6, RCP 4.5, and RCP 2.6, where the numbers correspond to the forced radiative flux imposed on the atmosphere to understand how the temperature of the atmosphere increases over the baseline number. Okay. And we also came up with the key conclusion that only if we restrict the radiative forcing to less than 2.6 watts per square meter, the temperature rise of the atmosphere or the global average temperature rise can be restricted to less than 1.5 degrees. Now, that is something which is shown by the green line on the left side of the graph. Now, one important outcome of this, which we briefly touched upon, is presented on the right hand side, please. Would like to seek your attention to the right hand side, wherein we talk about the different primary energy mixes which are going to provide the total energy requirement for the globe. Okay. Now, if you really look at RCP 8.5, then which is the bar in yellow color, you can see that coal forms the primary energy resource. So even today, good amount of the world, both developed and developing, is depending on coal for the primary energy. Okay. As we move from RCP 8.56 to 4.5 and finally to 2.6, one important consequence is that the contribution of coal comes down significantly for RCP 2.6. Would like to draw the attention of audience to the blue strips here. Now, these blue strips indicate how many exajoules of energy should be contributing from different energy resources under the RCP 2.6 scenario. Okay. Now, here you can see that solar, wind, and geothermal energy together can contribute up to 19 exajoules. Hydel energy can be up to 15 exajoules. Nuclear energy, 62 exajoules. Natural gas, 188 exajoules. Oil, 31 exajoules. What is most important is coal is 250 exajoules and bioenergy is 250 exajoules. Would like to once again emphasize coal and bioenergy both are 250 exajoules worth of contribution. What does this mean is that if we want to retain the temperature rise in the atmosphere to less than 1.5 degrees, then bioenergy contribution will have to be the maximum and on par with coal in order to satisfy the primary energy requirement. Okay, this is one of the key outcomes from RCP 2.6. Now, the question is why bioenergy should be a contributing factor here? Why should ultimately bioenergy be used? And if bioenergy is used, why will the rise in global temperature be restricted to under 1.5 degree centigrade? Now, one needs to really understand how biomass is actually grown. Okay, before I move ahead, I am on the slide which reads the context, why bioenergy. Somebody can confirm, please. Is this visible?
Yes, sir.
Okay, okay, thank you. So basically, we need to understand why bioenergy. Now, reflecting back on maybe some discussions during the secondary schools or higher secondary schools, maybe in biology chapter, we understand that biomass grows through a process of photosynthesis. Okay, biomass grows through a process of photosynthesis, and during the growth of biomass, carbon dioxide from the atmosphere is absorbed and gets fixed as the structure of the biomass. The leaf, the stem, so on, so forth, etc., will contain carbon as one of the major resource, and this carbon comes from atmospheric carbon dioxide. Okay, that is one of the important things. Now, if we burn biomass, then what happens is the same carbon dioxide, whatever is absorbed from the atmosphere, will be released back. Okay. What does this mean? This means that if we make use of biomass as an energy resource, then the net carbon dioxide emitted into the atmosphere is basically zero. Okay. Whatever is consumed, the same is again released back. But in the course of absorption and release back, you get your energy. Okay, so what exactly happens is that carbon dioxide, the bioresource pathway basically is carbon neutral. Okay. Now, if you really look at biomass as a chemical compound, just like we have typical stoichiometric formula for different chemical compounds like CO2 for carbon dioxide, H2O for water, CH4 for methane. Similarly, the typical composition of biomass is C1, H1.4 and O.6. Broadly, if you consider the complete structure of the biomass, this is the average chemical formula that comes. Now, out of this, when you do mass-based analysis, I would like to draw your attention to the fact that CHO number, whatever I have provided, they are all on mole basis. 1 mole of carbon, 1.4 moles of hydrogen, and 0.6 moles of atomic oxygen. Okay. Now, when you convert this biomass chemical structure on mass basis, it is seen that 52% of mass is in carbon, okay, and 6% by mass is hydrogen. So, what it effectively means is that when you grow tree or when you grow plants, every kg of plant that grows will have 52%, that is 520 grams of elemental carbon in it. Okay, every kg of carbon plant will contain 520 grams of elemental carbon. Now, what does this 520 grams of elemental carbon mean? Okay, now just I was mentioning that this carbon comes from atmospheric carbon dioxide being consumed. Okay, now if you really look at CO2 as a chemical compound, then every kilogram of or I would put it, every mole of carbon dioxide contains 1 mole of carbon and 2 moles of oxygen. Okay, that means that basically means if one if 1 kilogram of carbon is present, then if you burn that 1 kilogram of carbon, then it will release 42 by 12 moles or 44 by 12 kilograms of carbon dioxide into the atmosphere. That means if we grow 1 kg of biomass, then 1.9 kilograms of carbon dioxide equivalent are consumed from the atmosphere, which will in turn be reflecting as 520 grams of carbon in the biomass. So basically, for every kilogram of biomass that one grows, 520 grams of carbon from the atmosphere is consumed. That is 1.9 kilograms of carbon dioxide is consumed from the atmosphere. So every time we grow biomass or every time we grow tree, carbon dioxide from the atmosphere is removed, and reflecting back to my talk on the first day, the concentration of carbon dioxide from the atmosphere can come down. So that is the key feature of biomass. If you grow biomass, then carbon dioxide from the atmosphere will be removed, leading to reduction in the greenhouse effect and leading to, in turn, reduction in the global warming. So that is the beauty about biomass-based energy, that is bioenergy, because every time you grow biomass, you are taking out carbon dioxide from the atmosphere first before releasing it back. So the net energy or the net carbon dioxide emission into the atmosphere will be zero, while also giving you the necessary energy for the livelihood of human beings. Okay. Now, how can we make use of biomass or bioenergy? What are the different routes of using bioenergy? Now, bioenergy can be used through two different routes. One is thermochemical route, the other one is biochemical route. Now, biochemical route is pretty simple to understand, wherein we allow biomass to actually undergo typically anaerobic digestion. Okay, so when anaerobic digestion of biomass takes place, it leads to release of methane into the atmosphere. Now, this methane can be captured through appropriate technology, which is known as the biomass digesters. Then this methane can in turn be used for energy purpose. That is one way. The other way is a thermochemical route. Now, in this thermochemical route, the simplest thermochemical route that everyone would be aware of is to just burn the biomass. Okay, just burn the biomass. This has been the simplest way in which energy can be extracted from biomass. This has been in use since the time fire was discovered. Okay, since the time fire was discovered by Homo sapiens. So what we do in this case is we take any biomass in presence of sufficient air. If you ignite it, biomass will start burning, giving you heat energy. Okay, that is one very well established way of generating energy. Now, the other extreme is called as pyrolysis. Now, what is pyrolysis? Pyrolysis is basically a process wherein biomass is heated in absence of air. Okay. So for example, you take a cooker, in the cooker you put biomass and you create vacuum by removing all the air in it and you heat it. What exactly happens is whatever biomass is there, it will undergo what is called as thermal decomposition and it will get converted into some sort of oily substance, sticky oily substance and char. Okay, that is the process which is called as pyrolysis. So one case is combustion, wherein you get energy and products of combustion in gaseous form. The other one is pyrolysis, where you will get solid residue in the form of char and sticky liquid oils. Okay, that is pyrolysis. Now, in between these two, there is a process called as gasification, wherein if you give a small quantity of air to the thermochemical conversion process, then instead of getting converted into products of combustion like CO2 and H2O, or instead of getting converted into sticky oil and solid char, we get a gaseous compound which is a mixture of hydrogen, carbon monoxide, and methane. Okay, which is a mixture of hydrogen, carbon monoxide, and methane. Now, basically, this is a process called as biomass gasification. Okay, biomass gasification. So, basically, in gasification, what we are doing is we are converting biomass into a mixture of gaseous combustible compounds. I would like to draw your attention to the fact that hydrogen, carbon monoxide, and methane all are gaseous combustible components. So gasification is a process wherein we are converting solid biomass into a mixture of gaseous combustible compounds containing carbon monoxide, hydrogen, and methane. Okay. Now this process I am representing in the form of a stoichiometric equation as evident in this particular slide, please. As the title of the slide is bioresidue gasification. Now, in combustion process, you can see that the total air required for completely burning the biomass is 6 kilograms, approximately. Okay, 6 kilograms of air would be required to completely convert the biomass into products of combustion. Okay, now here you can see the equation. Okay, C1H1.4 and I am having 1.05 moles of O2 plus 3.76 N2. This together will come to 6 kilograms. Okay, now this will give carbon dioxide, nitrogen, and some water. Okay, now here you can see that I have marked carbon dioxide and nitrogen both are in blue color, basically because carbon dioxide and nitrogen are both products of combustion and they don't contain any calorific value. Okay, but this process will generate a lot of heat and this heat can be used for any thermal application. Like you can cook food or you can just use it in any industrial heat requirement purpose. Now, if we have a combustion process, in the combustion process, if we decrease the air supply, okay, if we decrease the air supply, then what happens is we go from combustion to gasification, and you can see the bottom equation. It generates hydrogen, carbon monoxide, and methane in the fraction of 20% hydrogen, 20% carbon monoxide, and 2% methane. Okay. One important factor to be understood here is in combustion we are giving 6 kilograms of air for every kg of biomass, but in this case, in case of gasification, we give only between 1.5 to 1.8 kilograms of air for every kg of biomass. That basically means we are reducing the amount of air that is supplied for the conversion process. So this process is called as substoichiometric combustion. I repeat, substoichiometric combustion. Okay. Stoichiometric combustion is when you give 6 kg. Substoichiometric combustion is when you give basically less than 6 kg, but in this case it is between 1.5 and 1.8 kg per kg of biomass. Okay. Now, as written in the equation, 20% hydrogen is generated, 20% carbon monoxide is generated, 2% methane is generated, plus 12% carbon dioxide is also there, and 46% nitrogen is also there. Okay. What is important is in combustion, the products of combustion have 0 calorific value, but in gasification, the products of combustion have 5 megajoules per kg calorific value. Okay, the calorific value contained in the gas is 5 megajoules per kg. Okay, now I am in the next slide where I am describing the process of gasification. Okay, I hope this slide is visible. Somebody can confirm, please.
Yes, sir.
Okay,
Yes,
thank
sir.
you. Yeah. Now, this particular slide is the typical representative diagram for gasification. Okay. On the left side, let me just pull out the pointer. Yeah. On the left side, that is here, you can see there is a reactor which is called as the gasification reactor. Now, this gasification reactor is basically a cylindrical element. Okay, it's a cylindrical element where air is drawn from the top as well as from the sides. Okay, biomass is given from the top, and from the side air nozzles we ignite the biomass that is introduced into the system. Okay, then this reactor is set under negative pressure by means of this blower. Okay, the moment the blower is started, this blower will start sucking the gas from this particular reactor, and because of this suction, air will enter from the top as well as from the sides, supporting the combustion. Okay, now, what is important here is the fact that the design of the reactor is created such that even though the top is open from, even though the reactor is open from the top as well as from the sides, only between 1.5 to 1.8 kg of air goes in for every kilogram of biomass. Okay. Now, let us suppose the reactor has a capacity of 100 kilograms, then the amount of air that will go in is around 150 to 180 kg. Similarly, if it is 1 ton, if the capacity of the reactor is 1 ton, then about 1500 to 1800 kg of air will go in. So what happens is this gasification will enter into what is called as gasification mode of thermochemical conversion. Okay. Now this gas comes from the bottom and it follows the path of low pressure. Okay. So the gas comes here, it goes like this. Now the gas that is coming out of the reactor is called as hot wet gas. Okay, hot and wet gas. The gas that is coming out of the reactor is at temperature of about 450 degrees, and it also contains some moisture. It contains some dust particles and it contains some tar. Okay, now, this gas, whatever comes out of the reactor, is first taken through what we call as a cyclone. Now, this cyclone is basically a gas cleaning system wherein, because of centrifugal action, some heavy particles, heavy dust particles are removed, and 80% clean gas is discharged. Okay, cyclones, a well-designed cyclone typically, a well-designed cyclone gasification cyclone typically has about 80% efficiency, and this basically means almost 80% of the dust particles are eliminated from the cyclone. Okay, 80% of dust is eliminated from the cyclone, and balance gas goes into the next element. Now, the next element is basically what we call as a scrubber. Okay. It is a scrubber wherein we spray high pressure water into this scrubber. Okay. Now, this high pressure water, when it is sprayed into the scrubber, it creates ejection action leading to movement of gas along with the water. So both water and gas will move down. This water is in the form of a fine spray, which is coming in at high pressure, and this mixture of gas and water will come into this bottom segment where it is called as a gas water separator, and here water is separated and it comes down and gas goes to the next element. Now in this scrubber, further cleaning and cooling of the gas will take place. Okay, further cleaning and cooling of the gas will take place, and that gas goes to the next scrubber. So there are two such scrubbers which receive water at 5 bar pressure and atmospheric temperature. Here, additional cooling of the gas will take place. Then the gas that is generated is further sent to a chilled scrubber. Okay? A chilled scrubber is basically a scrubber wherein same ejector action is provided, but with the water coming in at 8 degrees centigrade. Okay? Now, every time the gas is sprayed with high pressure water, then some of the condensable hydrocarbons which are present in the gas or tar which is present in the gas is eliminated, and lower the temperature, better will be the tar removal efficiency. So in the final scrubber, water at 8 degrees centigrade is sprayed on the gas, and the gas that comes out is very clean, but it is finally sent into one more element called as pre-coat filter, wherein it is basically like a filtration element containing some coated powders. And when the gas passes through this filtration element, a final level of cleaning will take place. So as the gas enters this pre-coat filter, it comes out extremely clean. Okay, so this is basically what we call as a gasification system. 1 minute. Yeah. Now, this gasification system can basically receive any type of biomass. That is why it is called as a feed agnostic system. Okay. So, for example, palm frond, coconut shell, bagasse, banana leaves, bamboo, wood chips, any of the typical biomass which is found in the country or anywhere else can be used as a fuel for this particular gasification system. Okay. Only requirement here is that loose biomass cannot be used for gasification, but the loose biomass should first be converted into briquettes, and then it can be subjected to gasification process. Okay. Now, these briquettes are required to have certain quality specifications. What are the quality specifications? Okay. One of the key requirement is that in these briquettes, ash content should be less than 10%, moisture content should be less than 10%, the particle density should be around 750 kg per cubic meter, and bulk density should be around 350 kg per cubic meter. So take any of the biomass that is available across the globe, convert it into briquettes which meet these specifications, and it can then be used for gasification process. Okay. Now, one of the important things is earlier in the course of gasification, I indicated that the gasification process generates 20% hydrogen, 20% carbon monoxide, and 2% methane. Now, suppose you want to increase the concentration of hydrogen to be generated. Okay, then what to do? Okay. Now, one of the important things is I told every kg of biomass will require about 1.5 kg of air for gasification. Now, if you really look at 1.5 kg of air, then we know that every kg of air contains about 230 grams of oxygen and approximately 770 grams of nitrogen. Okay, 230 grams oxygen, 770 grams of nitrogen. Okay. Now, in the gasification process, only oxygen takes part in the chemical reaction. Nitrogen doesn't take part in the chemical reaction. Okay. So, what we do is in the gasification process, instead of sending air, we can send for every kg of biomass, we can send only 330 grams of oxygen, because every kg contains 230, but we are sending 1.5 kg of air per kg of biomass. That means for every kg of biomass, we are sending approximately somewhere about 350 grams of oxygen. Okay, and the balance will be nitrogen. Now, what we can do is we can remove the nitrogen, send only the oxygen. Okay, send only 350 grams of oxygen into the reactor. Now, when we send only 350 grams of oxygen into the reactor, one of the major problems that happens is any combustion or any thermochemical conversion process in presence of pure oxygen is extremely intense. So gasification process cannot proceed normally. Okay. Now, in order to ensure that gasification process proceeds normally, instead of nitrogen, we supply steam. Okay. We supply steam. Now, what exactly happens is when we separate oxygen from air and give only oxygen and replace nitrogen by steam, the process gets converted from air gasification to oxy-steam gasification. Okay. The process changes from air gasification to oxy-steam gasification. Now, when we change this process from air gasification to oxy-steam gasification, one of the important changes that happens is, you can please look at the gas composition. In air gasification, we get 20% by volume hydrogen, but now you can see in oxy-steam gasification, the volume fraction of hydrogen increases to 50%. Okay. So from 20% hydrogen, you are now going to 50% hydrogen. Okay. That is the most important transition. Okay. And what is the other transition? Because of increase in hydrogen concentration, here you can see earlier the gas was having energy content of 5 megajoules per kg. Now the gas contains almost 11 megajoules per kg energy. So what happens is, in my air gasification system, I was sending air as the reactant. Every kg of biomass was consuming about 350 grams of oxygen, and balance that is 1150 grams of nitrogen. What I did, I retained the oxygen as it is, removed nitrogen, and in place of it, I introduced steam. When we did this, instead of air gasification, now we are carrying out oxy-steam gasification. And because of this, the hydrogen concentration increased by 2.5 times, and the calorific value of the gas increased by more than 100%. Okay. Now, I am giving some typical statistics here. Air gasification against oxy-steam gasification. You can take a look at it, please. Every kg of biomass, approximately 1.6 kg of air is given, and electricity required for operating the gasification system is about 0.1 unit. Okay. For every kg of biomass, you require only 0.1 unit of electricity, and this will produce 2.55 kilograms of producer gas. Okay. Each kg of that producer gas has got 5 megajoules of energy. Okay. So that is the gas composition I'm showing here, and the gas calorific value. When we move from air to oxy-steam gasification, the same 1 kg of biomass will consume the following units of oxygen, generating 1.4 kilograms of syngas. Okay. Now, once we generate steam, then what? Or once we generate syngas, then what? Once we generate producer gas, then what? Okay. Now, this particular plot gives the architecture for what we generally call as the biorefinery segment. Okay, we call this pathway as biorefinery segment. Okay. Now, gasification process, if it is operated in air mode, we produce what is called as producer gas. Now, this producer gas can be sent into an industrial burner wherein you generate thermal energy for any industrial applications. Now, the industrial applications can be for heat treatment process, for biscuit baking process, for tea drying process, for cooking food at industrial scale, or any such thing. So any application, even for boilers. So any application where thermal energy is required, this gas can be used. Now, the same gas can also be used for electricity generation. This is the most important thing, please. You can use it for electricity generation. Now, electricity generation is possible using pure 100% gas engines like natural gas engines, or even you can operate a diesel engine in dual fuel mode, wherein the producer gas will become what we call as a primary energy source, and diesel will become only the secondary energy source or pilot fuel. Okay. So this air gasification system can give you bioenergy in the form of bioelectricity or biothermal energy. Now, oxysteam gasification system, wherein we generate hydrogen-rich syngas, can be used for a variety of applications. The first application is generation of pure hydrogen. Okay, it is important to note that once we have synthetic gas which contains 50% by volume hydrogen, then this synthetic gas can be taken through a gas separation process to generate ultra high pure hydrogen. Okay, ultra high pure hydrogen. Now, once you generate ultra high pure hydrogen, then you can synthesize ammonia from that. Okay, what's ammonia? Ammonia is NH3. Okay, you can synthesize alcohols from that. I'm sure most of you might have heard there is something called as e-methanol. Okay, e-methanol is electrical methanol. E-methanol is basically it is called as electrical methanol, but it is called so because hydrogen is used along with carbon dioxide for generation of methyl alcohol. Okay, and this hydrogen, people generally think that the source of hydrogen is only from electrolysis, but we can generate hydrogen from biomass like what I'm showing now, react it with carbon dioxide to form e-alcohol like e-methanol. Okay, in this case, what is happening is you are taking out the carbon dioxide from atmosphere and converting that into a usable chemical energy. Then the generated hydrogen can be used in an industrial burner, typically industrial burner. The generated hydrogen can be used to generate electricity also. You can use it in an internal combustion engine, or you can use it in a PEM fuel cell. I will show some results about PEM fuel cells also as we go along. So you can generate electricity from it. Then the other important thing is the syngas, whatever is generated, if you reflect back on the previous slide, it contained 50% by volume hydrogen and 15% by volume carbon monoxide. Okay, H2 to CO ratio was almost 3 there. Okay, now any gas that contains H2 to CO ratio of 3 or more can be used for generation of aviation fuel. Okay, sustainable aviation fuel can be generated from this. Similarly, if you have a mixture of hydrogen, carbon monoxide, and carbon dioxide, then a ratio called as M can be defined. Okay, module. Okay. Now this M or module is having the definition of H2 minus CO2 divided by CO plus CO2. I repeat, M is equal to H2 minus CO2 divided by CO plus CO2. Now, if this ratio is 2, if this ratio is 2, then methyl alcohol can be generated. Okay, methyl alcohol can be generated. Now, if you really look at our syngas composition, it contains 30% carbon dioxide also. Now, if this 30% carbon dioxide can be reduced to less than 15%, less than 15%, then we get this module of 2, and this gas can be used to generate methyl alcohol. Okay. The next very important application of this syngas is in iron ore reduction. Okay. I'm sure all of you have heard iron ore is available in the form of Fe2O3. Okay. Iron ore is available in the form of Fe2O3, but what we require for manufacture of steel is Fe only. Okay. Fe2O3 must be converted to Fe. That means you have to remove oxygen from Fe2O3. Now, to remove oxygen from Fe2O3, today what is being done is coal is being used. Okay, coal acts like a reductant, and this reductant will remove the oxygen from Fe2O3. That is called as gray steel. Today, because of decarbonization, the emphasis is on generation of green steel. Okay. Now, for generation of this green steel, we make use of hydrogen and carbon monoxide. Both of these things will act like reductant to remove oxygen from Fe2O3. The process is Fe2O3 is converted into Fe3O4. Fe3O4 is converted into FeO. FeO is in turn converted into Fe. So it is a multi-step process, ultimately leading to conversion of or generation of iron. Okay, so the syngas generated can be used for synthesis of pure iron also. Now, one small input I would like to give here. Generally, when green steel is being spoken of, people say that hydrogen can be generated from electrolysis and that can be used for reduction of iron ore. Now the problem is hydrogen alone cannot be used for reduction of iron ore because the conversion of Fe2O3 to Fe using hydrogen is endothermic, whereas conversion of Fe2O3 to Fe using carbon monoxide is exothermic. So if you use hydrogen alone, then the temperature of the rotary kiln or vertical shaft furnace will go down and the reduction process will stop. So carbon monoxide is mandatorily required for conversion of Fe2O3 to Fe. Okay, so the syngas generated from biomass is the only route for reduction of iron and generation of green steel. Okay. Now on the right side here, I am giving you some statistics. Okay, the gas generated from biomass. Okay, every kg of biomass can give you 1 kilowatt hour of electricity. Okay, every kg can give you 1 kilowatt hour of electricity. Similarly, every kg of biomass will give you almost 3 kilowatt hour of thermal energy. 3 kilowatt of thermal energy. Similarly, if you want 1 kg of green hydrogen, we require 15 kg biomass. Okay, with 15 kg of biomass, you can generate 1 kg of green hydrogen. Similarly, every kg of green methanol will require about 2.5 kg of biomass. Okay. Similarly, 1 kg of 1 kg of biomass can give almost 4 kilograms of ammonia. Hmm? And every kg of biomass can lead to reduction of 1 kg of iron ore. Okay. Now, at Indian Institute of Science, we have established a pilot plant at 100 kg per hour capacity. Okay. I am on a slide which talks about pilot plant at IISc. Please, somebody can confirm if it is visible.
Yes, sir. Yes, sir.
Okay, thank you. So now the picture, whatever you are showing, is a pilot plant that we have established at IISc, and this is rated at 100 kilograms per hour. It can be operated in either air mode or it can be operated in at either oxy steam mode. When it is operated in air mode, okay, it produces 225 kilograms of producer gas every hour. It can generate 100 kilowatt hour of electricity or 350 kilowatt hour of thermal energy. The same system, when it is operated in oxy steam mode, again consumes 100 kilograms of biomass every hour. It generates 140 kilograms of syngas per hour. From this, we get between 5 to 6 kg of green hydrogen, or we can generate 50 kilograms of methanol, or we can generate 42 kilograms of reductant. Okay, the same plant can be operated in any of the modes. Now, I was saying that we are generating green hydrogen. Now, how are we separating this hydrogen from the other gases? Okay. Now, we generate synthetic gas from the gasification system shown on the left side. Now, the gas that is generated is passed through what is called as a vacuum pressure swing separation system. Okay. What is called as a vacuum pressure swing separation system. Now, this vacuum pressure swing separation system is basically a filtration system which acts like a filter for separating hydrogen from all other gases. Okay. Now this VPSA, as you can see, contains multiple towers, and these towers contain what are called as zeolites. Now these zeolites are essentially small pebbles which contain very high surface area and which are coated with certain proprietary material. Hmm. Now, this material is something which we don't develop at IISc. We purchase it from either Arkema in France or Honeywell Corporation, and we fill these towers with that particular bed material. And when we supply syngas at high pressure into these columns, okay, carbon monoxide, methane, and carbon dioxide will get absorbed by the bed material, and only hydrogen is released from the top of the column. Okay, all other gases are absorbed or retained, and hydrogen is released from the top. And this process continues to happen cyclically. Okay, this process continues to happen cyclically, and by means of proper control of the cycle, okay, by means of proper con- by means of proper control of the cycle, we continuously generate ultra high pure hydrogen. Okay, so hello, am I audible, please?
Yes, sir.
Yes,
Yes, sir.
sir. Yes, sir.
Yeah.
You are
Yes, sir.
audible, sir.
Yeah, there was some disturbance, so I thought, yeah. So, thank you. So, this VPSA system operates in a cyclical mode to separate ultra high pure hydrogen from all other gases. Now, we have developed this technology at Indian Institute of Science, both the oxysteam gasification system as well as the VPSA system. It is called as vacuum pressure swing adsorption based separation system. We have patent for both the things. Now, using this biomass gasification system and the VPSA system, today in IISc, we are in a position to generate green hydrogen, which is of proton exchange membrane fuel cell quality. Okay, proton exchange membrane fuel cell quality. Now, International Standards Organization defines the quality of PEM fuel cell hydrogen through the standard ISO 14687 2019. Okay. Now, as per this standard, the volumetric composition of hydrogen should be at a minimum of 99.97%, and there are 15 compounds which are designated as contaminants. Okay, there are 15 compounds which are designated as contaminants, and the third column you can see indicates the limit on the concentration of these compounds. For example, the hydrogen that is generated cannot contain moisture more than 5 ppm. Similarly, it cannot contain methane more than 100 ppm. Okay. Now, if you really come to carbon monoxide, you can see the concentration is limited to less than 200 ppb or 0.2 ppm. Similarly, look at sulfur. The sulfur compound should be less than 4 ppb. So on, so forth. So the ISO 14687 establishes a very stringent quality requirement, and the last column, what you can see, is the quality that has been achieved in our lab at IISc. Okay, water is not present. The total non-methane hydrocarbons, while the limit is 2, our measurements indicate only 1.236 ppm of contaminants to be present. Methane, it can be present at 100 ppm. We are having only 13.21 ppm. Similarly, you look at the total sulfur compounds. So while we require 4 ppb, what is measured is only 1.256 ppb. What does this basically mean is that the gas that we have generated in the lab at IISc using the oxysteam gasification process and the VPSA based process is hydrogen of PEM fuel cell quality. Okay, so we have been able to generate hydrogen of PEM fuel cell quality. Now, how do you measure these contaminants? The slide in this particular segment shows a train of gas chromatographs. Okay, we have created a train of gas chromatographs which are used for measuring different compounds at the respective limiting concentrations. Okay, see, if there are permanent gases like H2, CO, CH4, so on and so forth, which are present at percentage level, then they can be measured using online gas analyzers. Okay, they can be measured using online gas analyzers. However, for gases which are at ppm and ppb level, online gas analysis is not possible. We have to make use of chromatography based gas analysis systems. Okay, chromatography based systems. Now, the left top corner is basically GCMS. Okay, it's a mass spectroscopy. The second one is permanent gas analysis system where you can measure the concentration of carbon monoxide, methane, so on and so forth. The top right corner facility is used for measuring sulfur compounds. Now, one on the GCM on the GC you can see a black color element that is a heater. This heats the sulfur compounds to 900 degrees centigrade before taking into the columns for separation. The left bottom corner, we have what is called as a Fourier transform infrared spectroscope. It is used for measuring some compounds like aldehydes and so on. In the middle, we have what is called as a plasma emission based detection system. And on the right side is a typical GCTCD with an autosampler. So a range of infrastructure is required to even measure the quality of the hydrogen that is generated. Now, the hydrogen that has been generated has been passed through a proton exchange membrane fuel cell stack as shown in the figure here. Okay, it is a typical PEM fuel cell stack which we have purchased from fuel cell store. On the right hand side, you can see the specifications, and we have created a test setup for loading the fuel cell. Okay, now this is a test station which draws impedance or which applies impedance to the proton exchange membrane fuel cells, enabling drawing of current. The PEM fuel cell starts operating in what we call as open circuit mode. Then gradually, as we increase the resistance, the current drawn also or as we start decreasing the resistance, the current drawn also will start increasing. Okay, so this is the test station from Germany which is used to test the proton exchange membrane fuel cells. Now this is the result which shows the testing of the PEM fuel cell using the biohydrogen generated from the gasification process. Here you can see that on the x-axis, current is indicated. On the primary y-axis, voltage is indicated. On the secondary y-axis, power is indicated. Now, the black color line indicates operation of the PEM fuel cell using biohydrogen. The yellow color line indicates the PEM fuel cell operation using ultra-high pure hydrogen from bottled commercial sources. So, the yellow color line is from 99.999% pure hydrogen. The black color line is from biohydrogen generated in our lab. And here you can see that there is a near complete overlap of the graph. This means that the biohydrogen that we have generated is of sufficiently good quality, which can go into proton exchange membrane fuel cell. Okay. Now, as a part of project with Indian Oil Corporation, one such facility of generating biohydrogen will be deployed in New Delhi, and the hydrogen generated from that will be used for operating buses using PEM fuel cell. Okay. Now, while everyone talks about green hydrogen, one of the important factors that need to be understood is that as per the Government of India definition of green hydrogen, any hydrogen generation methodology which has got the effective or equivalent carbon dioxide emission of less than 2 kilograms will qualify as green hydrogen. Okay, I repeat here, any methodology or any method that has carbon dioxide intensity of less than 2 kilograms of carbon dioxide equivalent per kg of hydrogen generated will qualify as biohydrogen. Now here you look at the carbon intensity of this method. It is only 0.91 kg of carbon dioxide equivalent per kg of hydrogen generated. Okay. Now this number has been arrived at by considering both direct emissions and indirect emissions. Direct emission is basically the emission of carbon dioxide because of consumption of biomass. Indirect emission is basically the emission of carbon dioxide because of the electricity used for operating the gasifier and the VPSA, as well as transporting the biomass from up to 40-kilometer radius to a centralized location. So basically, the number 0.91 includes both scope 1 and scope 2 emissions of carbon dioxide. So in essence, the hydrogen generated from biomass based route qualifies as the green hydrogen as per the Government of India norms. Okay. Now, finally, at Indian Institute of Science, we have claimed almost 12 patents for variety of intermittent technologies associated with this biomass-based gasification system, as well as the vacuum pressure swing separation system for generation of green hydrogen. Okay. With this, I would like to close my presentation, please, and would be open to questions. Thank you so very much.
Rani from Government Engineering College, Dahod, Gujarat. So I wanted to know about the latest innovation in the hydrogen storage, especially the hydrogen is concerned. One of the major issue that may arise is its storing, or either you can say in way transportation. So which are the newer trends in the storing?
Yeah, it's a very good and relevant question, Dr. Jani. The basic thing is, as you rightly pointed out, storage of hydrogen is a key challenge. And today, a lot of research is going on in terms of the simplest method of storing hydrogen has been in terms of compressed storage. So today, what is being done is people are looking at 700 bar and even 1000 bar worth of storage. While there are safety concerns, but with evolution of low weight carbon fiber based cylinders, there is an attempt to store hydrogen in the form of high pressure compressed storage. The challenge here is compression of hydrogen is very difficult. Difficult in the sense it is not technologically difficult, but it is challenging from the point of view of energy consumption. Every kg of hydrogen which has 121 megajoules of energy, almost 12 megajoules of energy will get consumed if we use the compression route for storing hydrogen at 700 bar. So compression of hydrogen is a challenging feature, but compressed hydrogen storage is the most simplest and technologically advanced method. That is one thing that is currently being used even for dispensing hydrogen also. Apart from this, the next method that is being seriously considered is storage through metal hydrides. But again, here today, the state of the art is only about up to 4.5 percentage by weight of hydrogen can be stored, whereas the DOE target is up to 6%. If we can store more than 6% of hydrogen by weight through metal hydride route, then that will become highly economical. Some research is going on that particular front also. The next method of storage of hydrogen is through liquefaction. But liquefaction has its own challenges in the sense that you have to cool hydrogen to about 23 or even 18 Kelvin in order to liquefy it. And then the boil-off losses are very high, very, very high, significantly high. So cryogenic route, while has been established technically, but the boil-off losses are very high. So the next route that is being considered is through liquid organic hydrogen carriers. That is, convert hydrogen from pure hydrogen form into liquid organic carriers like methanol or ethanol. Once you convert it into methanol or ethanol, transportation becomes easy, it is safe. Only thing is you need to convert the methanol back into hydrogen. So as of now, technologically, it is well established process, but the conversion process from hydrogen to methanol, methanol to again hydrogen is still energy intensive. So these are the four routes. If you ask me in terms of technology readiness level, then the first simplest and most feasible route today is compressed storage. Second one is metal hydride. Third one is liquid organic hydrogen carriers. Last one would be through metal hydrides. Hope that answers your question, please.
Thank you, sir, for detailed information.
Thank you.
Any more questions from the participants?
Good evening, sir.
Good evening.
Thank you very much for this wonderful lecture, sir.
Thank you.
My question is, what are the major technological challenges in scaling of the green hydrogen production to meet the global energy demand?
See, today, as I was mentioning, there are only two sources of hydrogen generation. One is through water. The second one is through biomass. Okay. The fundamental challenge today for scaling up of hydrogen generation when it comes from a water-based approach is through the electrolysis route. See, electrolysis route today, whether it is through PEM electrolyzers or even alkaline electrolyzers, the amount of energy required is 60 kilowatts per kg of hydrogen. Okay. Now, this 60 kilowatt is significantly high. Where do we get 60 kilowatt of electricity, green electricity for generating green hydrogen is a major challenge. Today, none of the grids which are available across the globe are designed to handle complete green electricity. Okay? At the most, they can handle up to 40% of green electricity. Balance, base load has to come from thermal routes. So that is one of the major challenges. The second major challenge is the proton exchange membrane based electrolyzers are dependent on significantly large quantity of noble metals. Okay, you need platinum. Without platinum, even today, the electrolysis is not possible, and there are only limited resources available for platinum. So that is one of the other key challenges. Beyond this, the other challenge today is availability of pure water. Okay. So typically for generation of 1 kg of hydrogen, you require about 11 kg of water if this water is in pure deionized form. But as you are aware, pure water availability is extremely scarce. So today, when we go for RODM route for generation of water, which can be used in electrolyzers, the water demand is close to 45 kg or 45 liters. So 45 liters of water would be required for generation of 1 kg of hydrogen. So the way I see it, at one point of time, we had problem of food versus fuel. If we adopt large scale electrolyzers, then it will be water versus fuel. So we may not even have drinking water, sufficient drinking water. That is one of the major challenges. And when it comes to biomass based hydrogen, of course, there is a lot of biomass, excess biomass that is available, but that excess biomass will still not be sufficient to meet the complete global needs. So these are some of the challenges in regards to hydrogen generation. Please.
Friends, all of you switch on video for uploading proof for the AICTE portal. I am requesting all the participants, please switch on video for 30 seconds only. Thank you, sir, for your enlightened lecture on green hydrogen, green chemical, carbon negative bioresource pathway. Sir, you detailed explanation given on importance of bioenergy, production of bioenergy by using thermal biochemical methods, bioresidue gasification, and you explained in detail about various case studies like green hydrogen generation, quality analysis infrastructure, PEM field testing, and various patents obtained in IASC. Uh, so we are very grateful for your efforts and for presenting such a complex topic with clarity and precision, sir. Once again, thank you so much for your valuable contribution for this FDP, sir.
Thank you. Thank you, one and all. Good day.
Thank you, sir.